Hello, everyone. My name is Jeffrey Winters, Editor-in-Chief of Mechanical Engineering Magazine at ASME. Welcome to today's webinar, Check Valves and Relief Valves in Unsteady Flow. Can these ubiquitous devices pose a threat to your system? It's brought to you by our friends at Applied Flow Technology, a leader in the pipe flow modeling software market. With a primary focus on developing high-quality fluid flow analysis software, AFT has a comprehensive line of products for the analysis and design of piping and ducting systems. I will be your moderator for this event, but before we get started, let's get some simple housekeeping items out of the way. The console you are looking at is completely customizable. Every window you currently see, from the slide window to the Q&A panel, can be moved, enlarged, or collapsed. So if you want to change the look and feel of your console, go right ahead. If you have a question for our speaker, or actually speakers in this case, please enter it in the Q&A widget. We will get to as many as we can during the live Q&A portion at the end. If you need to leave early for any reason, don't worry. The presentation will be recorded and available for on-demand viewing starting tomorrow. Now let's get on to today's topic. Check valves and relief valves are present in systems throughout multiple industries. These devices are inherently transient in nature and react to unsteady flow conditions in potentially unexpected ways, and the consequences can be severe. This webinar discusses the basics of check valve and relief valves under unsteady flow conditions, and how typical selections can fail in common transient scenarios. The fundamentals behind the dynamic operation of these devices, practical models for use in simulations, simulation results, and design and selection of devices constructed with surge in mind are discussed. These topics also include why the unsteady behavior of check valves and relief valves can be dangerous, predicting this behavior with simulation, and design and selection basics. With that introduction out of the way, it's my pleasure to introduce our speakers for today's program, Scott Lang and Mark Dudley. Scott is a registered professional engineer in Colorado Springs, where he supports Applied Flow Technology as a lead software engineer, researching and developing numerical methods for modeling a variety of thermal fluid systems. Of particular interest to him is the prediction of turbo machine behavior and the general analysis of transient fluid flow. He holds a Bachelor of Science in Engineering with mechanical and engineering specialties from Colorado School of Mines. He's also contributed to the Hydraulic Institute Standards Committee, and he assists in organizing sessions for the ASME PVP conference. He's also authored or co-authored several peer-reviewed technical publications. His colleague, Mark Dudley, is a senior engineering software developer at Applied Flow Technology, also in Colorado Springs. His work at Applied Flow Technology is focused on implementing computational methods for piping systems, both incompressible and compressible. His contributions consistently revolve around numerical schemes for both heat transfer and slurry systems and steady and transient applications, as well as response analysis for surge prevention components. Mark has a Bachelor's of Science in Engineering Physics and a Master's of Science in Mechanical Engineering from the Colorado School of Mines. His master's research focused on multi-physics computational modeling for desalination systems. So, gentlemen, thank you for joining us today. And I believe we're starting with Scott. Take it away.
All right. Thank you very much, Jeffrey, for the great introduction. Yeah, so I won't talk about myself anymore. We'll jump right into the topic at hand here, which is check valves and relief valves in unsteady flow. But first, a little bit, about our company and what we do. So our mission and vision really is to help everyone understand and develop better fluid transfer systems, so piping systems. And of course, we have our products, our software packages that are the tools part of that, but we also place a lot of emphasis on education and service. So we're really proud of our support team here, how much we will help people understand their models, understand our products, things like that. And we also put a lot of time and resources into education. So things like these kinds of webinars, the papers that we wrote, and just general educational resources that we have available on our website. So why is flow analysis important? Probably not something I need to belabor for this audience, but obviously there are a lot of ways that this can help you. It's not just a tool to make sure that you've gotten a particular task done. It can also improve. They are not advancing. The slides aren't advancing here. I'm not sure if, are you able to advance them, Mark?
No, I have a audience button. Yeah.
Sorry for the technical difficulties here.
Hold on. I believe I can advance them. Let me just see if I can do this. Push to audience.
Okay, that did work.
Do you need the next slide?
All right, we got it. So sorry for that. So yeah, our mission and vision, we want to give you great tools, education, service, so that you can design good systems, safe, reliable, efficient systems. The reason why you want to use tools like ours, flow analysis, do these kinds of things, is for reliability, efficiency, safety, and of course, just ensuring the design works. So not only making new greenfield designs, but also just improving designs that you may already have. We serve a lot of different industries. I'm not going to name all of these, but everything from oil and gas pipelines to aerospace. Our software has been used on satellites, projects you've heard of, like the James Webb Space Telescope. Indirectly used in those kinds of systems. So a lot of cool stuff. General software, but a lot of applications there. We have a global reach. This past year, I believe, was our 30th anniversary. So we've been around for some time. We have a presence in more than 100 countries around the world, in large part supported by our network of partners. So 32 distribution partners all around the world that know and understand and sell our software. We also like to work with students, work with universities. So we have a lot of presence there, and student outreach, things like that. So who trusts our software? Obviously, a lot of companies here you would recognize. I'm not going to name them all, but same story. Different types of companies, a lot of industries, a lot of uses for our software, which is cool to see. Our products, we have this kind of matrix of products here. So Fathom, Arrow, Impulse, and Extreme. And the matrix here is that we have 2 products for liquids, 2 for gases, and on the opposite axis here, 2 for steady state, 2 for transients, essentially, rapid transients. So Fathom is our liquid steady state software. Arrow is similar steady state network software for gases. And then in the transient domain, we have Impulse and Extreme. We also have pulsation capabilities in those rapid transient softwares. So we have this pulsation frequency analysis, or PFA module, in both products to enable specific analysis in the frequency domain on high speed pulsation like you would see from a reciprocating device. We also have these, what we call here, slow transient modules. That is kind of a quasi steady state, over the day kind of change in maybe tank levels, something like that. What we're going to be talking about today is really the fast transients here that we analyze with AFT Impulse and AFT Extreme. So high speed acoustic transients, surge, water hammer, steam hammer, things like that. And in particular, our papers were really focused on AFT Impulse. So water hammer and surge. All right, so the topic at hand is a summary of these papers that we wrote and presented for the ASME PVP conference this past July in Seattle. The These were kind of sister papers with very similar title, as you can see, one for check valves and one for relief valves, discussing how these things behave in unsteady flow. And I do want to call out that, Mark and I are not the only authors here. We also worked on these with Jan Schroeder from the Netherlands and Mockveld Valves. So they make specialized valves, check valves, and surge relief valves for handling surge better. And also Dylan Whitty with Brown and Caldwell. He has done tons of modeling with our software. He's really an expert in building these kinds of systems and understanding the risks and strategies involved in sizing this kind of equipment. And then also on the relief valve paper, another colleague of ours, Devin Roraba, helped us out, and he actually presented that paper in Seattle. So those papers are on our website. You want to go take a look and read the whole thing. So it'll also be available, I believe, at the end of the webinar here for you. So motivation here, as Jeffrey kind of touched on, check valves, relief valves are common. You find these in a lot of different places. There's an issue in that they are often designed and specified strictly from steady state perspective. So how do I, have low pressure loss, things like that. But by nature, these are transient devices. Obviously a check valve, for it to be a check valve, has to close at some point. For a relief valve to be useful, it has to be able to open. And those opening and closing events are transients. And those events can cause, or do cause, waves that will travel throughout the system, pressure surge at the speed of sound. The entire system can be affected, and the level of that surge can be quite extreme. So very high pressures, very low pressures that can also cause problems. Different designs of these valves have different behavior. So you want to be able to obviously use a device that works well in the system, has not as much of a threat for problematic surge. And to do that, you need a tool to accurately predict what those surge levels are. So very high level basics on surge. Again, the idea is that they travel at some wave speed A here. It's basically the speed of sound in the system. So in the diagram here in the upper right, if you slam a valve closed on flow that's traveling from left to right, you'll see an increase in pressure spike on the upstream side of that valve, a drop in pressure on the downstream side. Both of those can cause a threat. And you can estimate the magnitude of that surge with this Joukowsky equation. Very simple equation. It's just an estimation. And a key thing is that it is not always conservative. And it's also very easy to misapply. In a situation like a valve closure like this, it's pretty easy to conceptualize what's going on. In a system, things get very complicated very quickly. So proper analysis requires a system level simulation. What we would recommend is the method of characteristics, a very common method used industry-wide in this kind of analysis, and the method that we use in AFT impulse. So we're using this Joukowsky equation as an easy to understand first order estimate of what's going on here, but we wouldn't recommend its use for application. Communication time is this concept that pressure waves take non-zero time to travel throughout the system. So anytime a wave is generated by a valve movement, for example, that wave is propagated throughout the system, and it will eventually run into something, a dead end, a tank, something that will cause it to reflect. And when it reflects, it will eventually travel back to the device that initiated the surge. So if that communication time is long enough, the surge levels at the initiating device, like the valve, don't have time to be relieved by the boundary, essentially. So any closures faster than communication time will actually see the same effective surge level as this idealized or Joukowsky surge. That essentially means that if your system's long enough, if the communication time is high enough, you can't just necessarily slow down the valve closure to mitigate the surge. It might have to be slowed down to an unreasonable degree. As I mentioned, AFT impulse, that's our software for modeling one-dimensional acoustic transients in liquid full piping networks. Uses the MOC, captures the effects of surge, communication time. We do all of this, in a very fundamental way, from root equations, conservation laws, things like that. So our estimation or our recommendation is, of course, to use AFD impulse. But even a stronger recommendation is just be sure you're simulating things and not guessing or estimating. It's very easy to miss things. All right. So an example here, just to maybe drive the message home, is what kind of magnitudes of surge are possible. So if you consider something like a pump trip flowing, initially in steady state flow through a valve. When you trip that pump, this flow is going to decrease. So just water, nothing fancy here. The valve closes or maybe opens against a reverse velocity here of 1 meter per second. So maybe during the pump trip, this is a check valve, for example, and you have 1 meter per second flow through this valve closes. The slam of that valve is going to generate surge that travels throughout the system, including maybe, let's say, a half-meter expansion loop some distance away, hundreds of meters away, not really related to the pumping skid or anything like that. And the question is, what kind of force might you see on that expansion loop? So from the Joukowsky method estimation, you can say that the pressure surge here is going to be about 1.2 megapascals. So that's pressure level above the steady state pressure or below. And a very simple way to estimate force is just taking that pressure surge and multiplying it by the cross-sectional area of that expansion loop. And in this example, that would give you about 235 kilonewtons or 53,000 pounds of force. This is not a contrived example. These are very realistic numbers. And it's a very moderate liquid flow rate. So not anything crazy here. These are very possible with surge. Okay, so that's all just a primer on surge, and why should you care about surge. Now what we're going to focus on is these devices themselves. So check valve obviously is just a device to prevent reverse flow. An ideal check valve is going to allow forward flow with zero pressure loss for any positive pressure differentials and zero reverse flow for any negative pressure differentials. It will also react instantly to changes in those conditions. Check valve slam, this is something that we're kind of defining here for the purposes of our discussion. Any real check valve takes time to close. And the fact that flow is reversing as it closes means it's going to close against some non-zero reverse flow. And that's going to generate surge, as that example showed. The generation of this surge, because of the closure of the check valve against that non-zero reverse flow, is what we're calling slam here. So there's also, maybe mechanical concerns of closing a valve too quickly, but that's not specifically what we're talking about. We're talking about the pressure surge. If a system has a check valve that closes faster than the communication time, we can call that an undamped check valve system. And most check valve systems probably fall in this domain because check valves do close very quickly, generally. In undamped systems, surge response is going to be pretty well approximated by the Joukowsky estimate. So you can see here in the figure, if you had flow decreasing linearly until it became negative, at some point that valve is going to begin closing, but you can basically approximate this as an instantaneous closure once it hits a certain reverse velocity for an undamped system. For damped kind of systems, things might be a little more complicated, or maybe even for an undamped system, you might want to look at this kind of physical model. So force balance model, these are screenshots from AFD Impulse, and you can set up, okay, here's my center of gravity, this is the buoyancy force, this is some torque, things like that. And these can capture some pretty cool physical behaviors, but this is still a simplification over reality. So the accuracy may not be what you might be expecting. There's definitely use cases for these, but it's not a solution for all cases. A simpler thing to do is to use what is called this dynamic characteristic model. So this represents several non-dimensional parameters related to the check valve. This first equation here was kind of an original proposal, not by us, by authors in the literature quite some decades ago, and that was simplified by additional people in the industry to this second equation on the bottom here, because certain non-dimensional groups there were recognized as maybe not that impactful. So instead, what the model is doing here is essentially saying there's a relationship or this dynamic characteristic between non-dimensional reverse velocity, that's the term on the left-hand side, and non-dimensional fluid acceleration, that's that first term on the right-hand side inside the brackets, and the general type of valve. So is this a swing check? Is this a ball check? Whatever the case may be. So really kind of a functional relationship between two numbers here. There's dimensional data and non-dimensional data, like a lot of these kinds of models. You see in the literature a lot of non-dimensional kind of data and work that can be easier to handle computationally, maybe easier to write some papers on, but it can actually hide real physical behavior. So two dimensionless characteristics can actually vary substantially between two valves of apparently the same type. Two valves with identical non-dimensional characteristics may behave dramatically different with peak, or have dramatically different peak absolute surge pressures. So that's a quick argument that we're making here. It's expanded a lot in the paper on you should really use dimensional data, even though you see maybe in the literature a lot non-dimensional data. It's safer to use dimensional data. It's also important to keep in mind that this dynamic characteristic model is empirical. So that curve, the relationship between those two values is generated by test data. So take care if you're using just a curve with no data points. This figure here is an example from the paper of one of the kind of situations you might find just in the literature. This is very typical that you just see the line here, but the real data has obviously a pretty significant scatter. So the check valve behavior is pretty chaotic, and this model should be thought of as a median behavior, not a guarantee. There's also a lot of variability within a particular check valve type. So sometimes you'll see charts kind of like this one that are charting closure velocity versus deceleration. And it says this is the line for maybe a nozzle ring valve. And there's one line on the chart. And the reason you may see that is because that chart may be non-dimensional. But that non-dimensionality kind of hides the fact that there's actually quite a lot of spread in the data here. So this chart is just showing that, hey, even though you have the same type of valve, depending on the actual manufacturer of that valve, the size of the valve, the specifics at play, behavior may vary quite a lot. There's a lot of historical data here. So this is that data I mentioned that has been generated via testing to create these dynamic characteristics. It's not necessarily common, but there's enough of it that we felt it was useful to create this paper and compile an amount, as much as we could of these different characteristics. But some data can be lost. So when it gets republicized, you might lose those actual data points. You might have only the curve. You might lose the actual test conditions and only have non-dimensional data, things like that. So we cataloged all of this to try to quantify, what is the data quality and what does the variability of the data look like. So this is a very quick kind of summary of all of that research that we did. And this chart is kind of summarizing an approximate range for different characteristics that we found based off of the type of check valve. So the idea here is it's showing you that maybe a swing check valve is towards the worst end of check valves in terms of surge behavior because it has the kind of the highest potential closure velocity here, which would translate into pressure surge levels. And the piston and ring type valves are kind of towards the lower end. So it's showing you that different types may be better, but it's also showing you that there's a lot of overlap here and a lot of range. So you have to be careful not just saying, hey, this is the characteristic for a ball check. Pretty quickly here, I'm going to go through, how do you calculate this deceleration? Because we have this simple chart here with this nice line of saying, hey, maybe I have velocity decreasing over time because maybe due to a pump trip. And that's going to correspond, of course, since this is just a linear slope, a constant deceleration. And it's pretty intuitive that I can just use that to look up a deceleration on the dynamic characteristic and get an associated closure velocity. And then from that, determine essentially a pressure surge level. So that's pretty straightforward, but realistically, you have a complicated deceleration profile. So it's less clear what value to use. And again, I'm going to go through this pretty quickly just to emphasize that there's a lot of options here. One option is to just start measuring at the beginning of the simulation and stop when flow reverses and use that slope to estimate the deceleration. But that might miss when the closure event actually begins. So you can try to guess, well, when did the velocity start decreasing significantly? That requires some kind of metric. It may still not be related to closure. You can try using an instantaneous acceleration value, but with any kind of numerical simulation, that's risky because you can get some erroneous values just due to simulation noise. You can try checking for the last significant reversal, but if that's above some fully open velocity, that's the velocity needed to keep the check valve completely open during steady flow. This may not be meaningful because any changes in velocity above that point aren't resulting in valve movement. You might just use a specified time before reversal, so a sliding window that's just checking things. But now we also have this concept of natural closure time, which is essentially if you, in stagnant flow, just let a check valve close, how long does it take to close? There's a relationship between that and how much you can realistically expect it to basically be considered as being forced to close by the transients in the system as opposed to just naturally closing. So complicated relationship there, potentially. You could also just say, well, let's just start tracking when this minimum velocity is reached. So it can't close before that, but maybe it is closing. But again, it's not necessarily closing. So a lot of options there. I went through that quickly. And our recommendation here is that you shouldn't use velocities above that minimum to fully open velocity. The valve is fully open and can't be undergoing any kind of movement. And the deceleration you should use should be from when it drops below that minimum to fully open line. If the time to closure is above or from the above point is longer than the natural closure time, you should use a specified time or check that specified time. And whichever deceleration is stronger than the above, use that instead. So it is confusing. The summary, this is a lot easier to see, in some diagrams and stuff. But the summary is basically there's a few options to calculate deceleration, and you want to use the most severe one that you can. Calculate with stability. So you don't want to do anything numerically suspect, but you want to say this is a conservative approach. I want to take the most severe deceleration that's reasonable to calculate and use that. All right, so the characteristic model in Impulse. This is just a screenshot from our check valve model. And you can see a number of lines in the lower right of this figure. Those different options for dimensional check valve curves. So you can choose one of these. You can choose a non-dimensional curves, all just from the literature, and run with those. But you can also define your own characteristic. It's pretty simple to do all of this. It's really just, give us a curve, give us maybe a fully open or minimum to fully open velocity, and you can run with it. And Impulse will give you some estimation of the surge levels when that closes. So I said a lot about, hey, this is an empirical model. It's not great. You want to do things conservatively, so that brings up the question, well, how accurate is it? This is from another paper that some colleagues of ours generated, both at AFTN and industry partners. Essentially a case study on a municipal water pumping station in Barcelona. And the idea here was there were two check valves in the field, and they were looking at which one of these will be better for the system. Do we need to replace the swing check with the nozzle check? So there's field data here, measured in black there, and data from Impulse measured in blue. And the agreement is pretty good here. I would also note that the scale on these two graphs is the same. So you can see a pretty dramatic reduction in the surge behavior here with the nozzle check valve as opposed to the swing check valve. So that would have a dynamic characteristic that's lower on that other graph. And I'm not the expert on selecting hardware. Our co-author that's not here, Jans, is. So just briefly, I'm going to touch on valve selection. There's trade-offs between steady and dynamic performance, but it is incorrect to say that a check valve has to have good performance in one, that you either have to get a good steady state valve with low pressure loss or a check valve that works well in surge. A engineered valve can have excellent all-around performance. For liquid service, I would say our general recommendation for valve selection is ensure the dynamic performance is acceptable. That's a pretty broad statement, but it's a quick check that you can do, especially if you're trying to do a conservative or a rough first order check. And also, I would say, keep in mind that not all check valves require a highly specialized engineered valve. You might do this quick check and see that, the worst case surge here is more than acceptable. That's fine. We're not trying to argue that every valve needs to be specialized or that every situation needs as much protection. But it may not be very clear which system has a critical check valve. It's not just this system is important, so it needs a critical check on the check valves, or this system can stand surge. You do really need to do this second step, which is look at the dynamic performance, run a quick study, see if it is going to cause some problems, and then make the second judgment on criticality. All right, and with that, I will pass it over to Mark to talk about relief valves.
Sure. Yeah. So we'll just kind of start from the basics.
This is what we're doing.
Oh, cool. We should do that instead. Sorry, give us 1 second here. Okay. So starting from the basics, talking about what are we considering a relief valve. So a relief valve is just any kind of device that is specifically made to open and mitigate an overpressure, any kind of high pressure. Conventionally, what you usually hear considered as a relief valve is overpressures that are based off of slow transients. So slow transients would fall more in line with, you see them a lot with like pump deadhead kind of stuff. So pump deadhead, thermal expansion of liquids, you'll find them a lot in compressible flow for like tacked on a boiler kind of thing. You find them on water heaters and stuff like that a lot. Within liquids, you usually find them for like fire relief cases and things like that. There's really two different types that we consider, at AFT. You have reclosing devices, which is a relief valve that is able to crack open relief fluid and then drop the pressure and then reseat, and then it can be used again. Usually those have different names, relief valve and PRD, or pressure relief device, or PRV. In some industries, they refer to them as safety valves and safety relief valves. They function very, very much the same, and they have the same sort of behavior, but they have different names depending on the industry that you're in. I'm going to refer to them as just a PRD going forward. And then the other alternative is a non-reclosing device. Obviously, that's your rupture disc or your rupture pin, something that once you exceed your set point, your pressure set point, then it will break the device and essentially just relieve fluid, but then it needs to be replaced with something else. Something that's really important to consider here is, we talked a little bit about slow transients and faster transients. Most relief valve designs, even though they are designed for overpressures, they will not react fast enough to mitigate surge. And in fact, there's a lot of guidelines and standards that are out there for relief valves and relief devices that just recommend that, you shouldn't really consider the two of them within the same system. If you have a system that is prone to surge, then you should avoid it. And that's true for API standard 521. That's true for Emerson's handbook on relief valve design, a variety of other safety relief valve handbooks, including ASME and the international codes. But I think that it should be pretty clear that surge interaction with relief devices is unavoidable. And relief devices, because they are passive transient, they will react to surge in your system or any kind of overpressure. They can also cause surge as well. Relief valves that open, they will try to open in order to counteract surge, but the opening can actually cause surge or instabilities, and those interactions with the rest of your system can quickly get out of hand. So it's important to remember that we want to weigh the severity of what is the relief valve doing versus what is the surge that your system is seeing, what are other causes of fast transients, things like that, which is why we advocate very heavily that you want to use a system level analysis for it, right? So similar to what Scott said, using method characteristics or something else in order to represent your system from a computational standpoint is incredibly important, and really when we're interested in doing it, whether it's for a check valve or for a relief valve, really you want to have your main focus is on the system itself. We're more interested in ensuring that the valve is going to be represented accurately with respect to the system, and so that with that in mind, we'll use the MOC for the actual system, and then we need a way to basically convert that back and forth with the relief valve. So there's a handful of different ways really to do it from a one-dimensional standpoint, which is most of what surge analysis is focused on. You might just use a simple loss equation, so any kind of valve orifice, some kind of loss equation like that relates a loss coefficient or valve coefficient to pressure loss and flow. You might use a lift performance curve or some kind of manufacturer provided data that will tell you how much pressure loss you're going to get based off of your flow. And if you have a more in-depth investigation that needs to happen, then you'll start to see force balances that are being accounted for on relief valve plugs. And usually you just want some kind of a representation for inlet pressure to whatever your relief valve opening percentage is. In our experience, most of what you see are these top two. The force balance, you find more often vibration analysis, and sometimes you'll get a little bit in pulsation kind of stuff. But for surge analysis, it's a little too in depth to go for a force balance. So, and then within the context of AFT impulse, so we have a very in-depth relief valve that we advocate for, and it's defined basically with two different concepts in mind, which is when does the valve open, and then once the valve is open, what kind of pressure losses are you going to see based off of flow rates, kind of what we talked about. We have opportunities to represent an internal valve or exit valve, whether you're considering the outlet side of the relief valve as part of your simulation or not, you just jettison to the atmosphere or ambient, or do you want to ignore the relief valve standing pipe altogether? Keep it in line. We have a variety of different profiles, opening and closing characteristics, and then also the set points, which is the bread and butter of really how relief valves function. We care about when your pressure set point is exceeded so that we can crack the valve. We care about the overpressure, so where it has maximum lift. And then we also care about the blowdown pressures. Blowdown pressure is when the valve is essentially reseated. And obviously for a non-reclosing device, you would not have blowdown pressure. And then we also have the options for rate limits and other loss models and stuff like that as well to characterize, well, what kind of a valve is this? What kind of pressure losses would I see? So I'm going to just take a look at a couple of different examples here of how a relief valve might change depending on the system that you're seeing, the surge that you're seeing, things like that, and how does that kind of inform our process for what kind of design considerations would you want to take? So the first one is a classic relief valve case, which is relief valve sizzle or simmer or chatter, and kind of simulating this. So we have a simplified example here of a 2,000 foot long pipe that is at the discharge of a pump that's outputting about 100 psi. Nothing crazy, but it's going to a exit valve that is discharging to atmosphere. And our exit valve, we're just going to slam it within basically 100 milliseconds. And that slam is going to cause a surge wave to propagate back from the valve at the downstream side up towards the discharge side of our pump. About 500 feet into the line, we're also going to put down this relief valve standing pipe that's just about 5 feet long. But we've sized the relief valve in case of a pump deadhead event. So not in case, not trying to do anything with the surge. And the relief valve is going to open over the course of a second with a set pressure that's just above where our ideal discharge pressure is. And in order to see, what kind of pressure response would you have from this? What you end up seeing here is that the relief valve will actually open over the course of half a second. And if you take a look at the graph here on the side, this is a transient response at the inlet of the relief valve. And the red line is the static pressure, which you can see is remaining more or less constant until that surge wave hits it, and then it dramatically raises the inlet pressure. Once it reaches above that set point, you see the blue line is the velocity that is passing out of that relief valve. And you see that the valve cracks open, and as it begins to relieve more and more fluid, eventually it overcomes that surge pressure that is in the actual relief valve itself. And what ends up happening is the frictional losses from the standing pipe will overcome the surge in pressure as it gets higher and higher, and you end up with a chattering situation as the pressure raises, which causes the relief valve to open, which causes the pressure to drop as it relieves fluid, which causes the pressure to raise once again, and you end up with an unstable situation here. So this type of effect is what you would see from some type of relief valve chattering situation. Usually, relief valve chattering is a result of kind of a missized situation, right? We have a relief valve that's sized for something else that's trying to respond to a surge wave that's incoming, right? And that instability will cause more problems as it goes. So then it begs the question of, well, why can't we use a relief device in order to mitigate surge? And in order to kind of take a look at that, what we're going to do is we're going to take a very similar situation here. We have just that same 2,000 foot long pipe, but we've raised the supply pressure just so that we can take a look at the system a little bit better. And we still have the exit valve that's slamming within 100 milliseconds, but now the relief valve, we've designed it in order to respond to the pressure wave that's incoming, right? So you have a 50 millisecond opening, which, if you're familiar with relief valves, is dramatically fast for a relief valve. And we have a set pressure and a reseat pressure that are equivalent, but it is essentially once it goes above that 300 psi threshold, the relief valve will open up to 330 psi above it. If we take a look at the response here, the transient behavior, comparing the blue line here, which would be without the pressure relief device, and the red line to this surge designed relief device, you see that it's curbing. The pressure spike pretty dramatically. Without the pressure relief device, you have a psi of about 1,000 psi. That's of that first surge that's coming by, and then as the downsurge comes back, it's causing it to drop well into the range of cavitation range, and now you start to run into some other issues. This pressure relief device that we've put in, that we've very quickly opened, it is able to kind of stop the peak of that surge wave from coming by, and it reduces the pressure waves that you're seeing. Okay, well, so then why wouldn't this be? Why is this a bad thing? Why can't we use PRDs for a surge? Well, that requires us to know a lot of information about the surge. This specifically, you have to know the magnitude that's coming by. You have to know the timing, and as a result, the kind of the steepness of that wave. Usually, conventional relief valves, as I said, 50 milliseconds is very fast for most conventional relief valves. That's not going to be fast enough to actually act on this. And so you need something that is a little bit more reactionary, but it requires a kind of a nice system in order to play ball with the surge wave. And just kind of to drive that point home, we have the same system here, but instead of opening over 50 milliseconds, we're comparing 50 milliseconds versus 100 milliseconds versus 200 milliseconds for a full opening. And what you can see here is that the difference in that is that wave of how much of that peak is actually shaved off changes dramatically if you get into a more realistic conventional PRD opening speed. And so that begs the question of, well, it looks like there is something here that, you could take a conventional PRD or something similar to that type of behavior, and you could mitigate surge with it. And so that's kind of where we get to the next component of this, which is more in line with what our collaborators with Mockfeld valves, what they work on specifically. And it leads to the surge relief valve. So the surge relief valve is something that is different from if you've ever heard of a surge anticipator valve. Surge relief valve is specifically for surge relief. It's not, that's the overpressure event that it's designed for. It's not for other scenarios. It's a unique relief valve that's better understood as a pressure sustaining valve. And without getting into the nitty gritty of exactly how this works, because I'm not the expert on the surge relief valve, essentially as the forces, as the pressure at the inlet of the surge relief valve exceeds your set point, then what you'll end up seeing is it will breach the set point, which will trigger a pilot. And when that pilot is triggered, it will vent out the atmosphere and allow a massive amount of flow that corresponds to whatever the surge wave you would see to flow through the relief valve. And specifically, it does so proportionally to the actual surge wave itself. And the important part about this is that this pilot is fast acting enough to where it can actually handle the surge wave as it's passing that upsurge. And so it is it's unique in the sense that it is a pressure relief device, but it is not a conventional pressure relief device. And so this is something that is very specifically targeted for surge. And in order to represent something like that, even within our own software, we have to kind of treat it a little differently. And so instead here, what we have is we have the same kind of system that we've had before. We have 300 PSI going to an exit valve. But instead of having a relief valve device in there, we've had to replace it with something that is more representative of the surge relief valve, which for us is a control valve. And is a control valve that is attempting to maintain a pressure at the upstream side, so closer to where the surge would be coming in. For this representation, we still have it opening at 50 milliseconds, which is more on par for a surge relief valve. We've specifically sized it to mitigate the surge wave. That's what it's intended to do. And with the surge pressure of a set pressure of 330 psia. And essentially what we end up seeing here is that when we compare the surge relief valve, this case that's shown here, to the cases that we've seen in the past, which would be the case where there's no relief valve versus an idealized conventional relief valve that's opening a little too fast for most conventional PRDs, what we see that the surge relief valve effectively is attempting to shave that peak off completely. It reacts fast enough and accurately enough to where the pressure, the differences in that kind of spike pressure that you see on the upsurge is 1,000 psi for the case with no PRD to the red case here, which is about 500 psia. And then that's cutting down to the surge relief valve, which is the blue line, which, if you can tell, is not even breaching 400 psia, right? And so what we see is that the surge relief valve is able to handle this type of behavior on the upsurge. But for the downsurge, what we could see is that our simulations, when we were trying to represent this, was not accurate enough for the downsurge that's coming back, right? As you can see that the blue line dips a little low and pretty close to the cavitation range for that downsurge as it comes flying back. So there's obviously a little bit of finagling that you have to do with this type of model. But this is a very, very specific and unique case of where you could take this type of relief device and use it in order for surge mitigation. So in order to conclude, as Scott had talked about, when it comes to check valve slam, that's what we call a check valve that's closing rapidly against some kind of non-zero reverse flow, and relief valve activation, or any kind of initiation of transient, that could be potentially dangerous for pressure surges, either in addition to incoming pressure surge or as a kind of causer of that. A lot of times they're overlooked because they're not primary events. Those are not usually the things that you would see initiating surge. They are things that react and they get exacerbated, but very often they are kind of overlooked as a result by most analysts. What we notice is that for rule of thumb approaches, what we see is that even the most seasoned analyst or whatever has troubles with trying to handle these types of surge system designs. So, and then specifically something that is advocated in a variety of literature, but we need to advocate it here just in case that was kind of the takeaway, is the check valves and conventional relief devices, they are not surge mitigation tools. They should not be used as a primary surge mitigation device. You require specialized equipment in order to mitigate surge for relief devices, and for check valves, that has to be a part of the design considerations, essentially, in order to try and mitigate those separately. However, you still need to consider them for surge analysis, but they can't be your solution to the surge analysis. So, and I believe with that, I thank you to ASDME here, and I believe that's all we had, Jeff.
Well, we have time for a few questions too. So the folks have been writing in. If you have any additional questions, you might be able to sneak them in before we take off. But let's get started with what we've got. First of all, are there any simplified methods to do a sort of a quick and dirty estimation for the deleterious effects of valve closing or openings?
Right. That is a great question. That's kind of where we're coming from with like the Joukowsky equation, and that's a very common thing that you'll find in textbooks about how do you calculate surges. Joukowsky equation is always there, and I would say that is the quick and dirty kind of estimate. Is you can say, well, I expect there to be at a peak through this valve, relief valve or check valve, this much flow feet per second, this velocity. And I'm going to assume that that's instantly stopped. And I'm going to plug that into the Joukowsky equation to get a surge level. Again, that is the kind of the standard quick and dirty estimation. Sometimes it's conservative, but there are cases where it is not. So you want to be careful with that. I would want to make sure everyone understands that if you just use that across the board, you can get into trouble.
Fair enough. We have another question that came in. Would the use of spring or weight-assisted closing for a swing check help reduce the forces in it?
It depends on the application, as far as I'm aware. But I believe they can assist with that type of thing, but it might not necessarily. You still have the problem of like valve closure speed, things like that, that can exacerbate other problems, specifically within surge. So it can help reduce the forces, but it's case by case. Usually, correct check valve for the correct system kind of thing is more what you want to do. So.
Okay, that's good. Another question that came in: Can the AFT model the PRV performance impacts associated with the flow or pressure losses caused by installing a PRV on a reduced line size that has a smaller inlet area than the PRV inlet?
I believe, Scott, you probably have to correct me, but yes, I believe that we do have that type of capability. We have a lot of customization that you can do relative to the PRD junction, which would allow that type of which would allow that type of consideration, as well as with the actual interaction with the pipe that is upstream of it, type of thing. So
right, and if I'm interpreting the question right, that's what I was thinking is, it's a general kind of configuration tool, so you can put in the relief valve and connect it to whatever piping you want. So if the piping has a lower line size, it will kind of handle that just by nature of the tool.
Yeah.
Okay, good. We have another one that's come in. Can vacuum relief cases be handled? It's less common than pressure release, but the failure mode may be buckling or collapsing of a vessel.
I would assume that you mean handled within like AFT impulse, and the answer is yes. We do we do allow for that kind of accounting with like cavitation, things like that. Probably not necessarily the that exact same case or whatever, but as in terms of a system kind of response, if you ever would go into vacuum where you get to very, very low pressures, yes, that can be handled.
Yeah, and I would add on in terms of the typical way that you would mitigate that would be with something like an air valve or a vacuum breaker valve. Very similar concerns with those as to the topic at hand of if it opens too quickly or closes again too quickly, you get surge. And an additional thing here, since you mentioned vacuum cases, we mentioned a couple of times in this presentation that there's high surges and low surges. Those are equally important, and they often come in tandem. If you're interested in kind of how do you look at low pressure, we do have another paper on our website titled something like "Addressing Low Pressure Transient." That's a good just kind of overview of how does it happen, what do you do about it.
Okay. Well, gentlemen, I think people should check that out. We are at the top of the hour now, and that's all the time we have. So I would like to thank both you gentlemen for joining us today, Scott and Mark. We would like to thank all of you out in webinar land for joining us today. I hope, and we all hope, that it was valuable for you. Again, special thanks to Scott and Mark for their time and their expert insights, and to our sponsor, Applied Flow Technology, for their support. Without them, this webinar would not be available to you. If you missed any part of this presentation, it will be archived shortly, so you can view it again or refer it to someone else. That's about all the time we have today. My name is Jeffrey Winters with ASME. Thank you for your time and attention. Have a great rest of your afternoon.
Thank you, everyone.